Good afternoon.
Good afternoon, sir.
Good afternoon. So in my earlier email, I mentioned that this particular course requires some knowledge in microbiology as well as biochemistry a little bit. Then I checked the course of studies also, but unfortunately they have not mentioned anything in that course of study. So basically this course has prerequisites, and in our internal document I could see that they have mentioned about 3 different courses. One is the general microbiology, and then biochemistry, and also bioprocess engineering. Only thing is those who are from other departments and also 2020 entry students, they may have a little bit of difficulty to understand few terminologies. So if you are okay to manage it, then you can still continue with this course. But if you feel that it is a little difficult to manage, then you still have time because ad drop period is still going on. So if you want, you can drop this course and then take a different course then. This is totally up to you. Because as per course of studies, the printing mistake was there, because that's why they couldn't put these 2-3 prerequisite. Otherwise, in our internal document, I could see this course actually has mentioned about 3 different courses as prerequisites. So the 2019 entry student will not have much problem because they have already taken all these courses. But 2020 entry student will definitely have a little bit of difficulty, and also students from other department, they will also have issue. So whatever you feel, means if you feel it is comfortable with you, then you can just continue, else you need to drop this course. Okay, so in the last class we have mentioned about significance of stoichiometric formula, because in any given process, if you know the reaction, and if you know the balanced reaction scheme, then actually it is easy for you to calculate raw material required for that particular process. And most of the cases we try to keep a little bit of excess reactant just to make sure that you are not having any limitation of a reactant in the process. So if you know the exact amount of reactant required, then only you can add some extra amount to maintain excess reactant. And to do that, you need to actually know the complete molecular formula of this different components involved in the stoichiometric equation or in the chemical reaction. So one of the crucial component in biochemical reaction is your cell biomass. So cell biomass could be bacteria, could be your plant cell, could be a animal cell, and also you can have other microorganism like fungi. So if you know the molecular formula of that biomass, because here in biological system, you'll have substrate, then say oxygen, or without oxygen, that is also possible. And then you'll have biomass, then you'll get more biomass plus product plus water or carbon dioxide. That's a common reaction scheme. And within the substrate, you will have carbon, nitrogen, phosphorus, and so many other nutrients required for bacterial growth. And some cases you can get intercellular product. In that case, biomass will contain the product. In some cases, you will get extracellular product, so you will have biomass plus product. Now, to know the molecular formula of biomass, because if you see substrate, as we mentioned earlier, one substrate could be glucose, that is your carbon source. You can use ammonia as your nitrogen source, phosphate, some phosphate salt as your phosphorus source. So the substrate, whatever substrate you will use, you can actually have a reasonable idea of the formula of the substrate. Similarly, product, if you are thinking of producing ethanol, methanol, or any other product, you can get good idea about the product also. So you can get the molecular formula of the product. The rest of the components are well defined. Now, only problem is with the biomass where molecular formula may not be known to you. So to know the molecular formula, we need to actually check the composition of different element present in the biomass. So mostly in biomass, we get some elements which are known as major elements because their concentration will be much, much higher compared to any other elements. So carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, they are also there, but compared to carbon, hydrogen, oxygen, nitrogen, phosphorus or sulfur concentration will not be that high. And apart from these elements, you will also have lot of other micro elements. So these are all major or macro elements. And apart from them, whatever elements you have in a cell, they will be clubbed as a group called micro elements. Now, if we can get composition in terms of carbon, hydrogen, oxygen, nitrogen, then actually we can get reasonable idea about the molecular formula of the biomass. And as I mentioned, it may not be the means this major elements may not represent the true molecular formula. You may have so many other components also, but their concentration will not be that high. So when you try to compare molecular weight, then you will find maybe 95 to 90-80%, 95 to 98% is contributed by this major elements or macro elements, and only 5 to 2%, or you can say 2 to 5%, is contributed by micro elements. So their contribution is much smaller, whereas the major element has significant contribution. So E. coli is one of the favored organism in bioprocess engineering because you can actually modify E. coli and make different recombinant strain of E. coli. Similarly, Saccharomyces cerevisiae is also another yeast that is a group of fungi. So in Saccharomyces cerevisiae, that is also a well-known platform which can be genetically modified and you can use it for production of different bioproducts. So E. coli as well as yeast, both of them are, yeast means Saccharomyces cerevisiae, both of them are very well-known host organism to produce different bioproducts. Now, when you try to estimate the composition in terms of major elements, then you can see E. coli as well as yeast, carbon content is 50%, oxygen 20 to 34%, nitrogen 14% to 8%, hydrogen 8%, 6%. And then you also have all other elements like phosphorus, sulfur, sodium, potassium, and other elements. Now we are just considering the first four elements which has significant amount. So whenever you try to get the weight of biomass, you have two options. One is get the biomass from the beaker, like you first you grow the culture in a conical flask. So for growth, they will require water, they will require different substrate like carbon source, nitrogen source, phosphorus source, different vitamins, minerals. So you incubate them at their optimum growth temperature. Suppose we are growing E. coli, it prefers 30 degrees centigrade. And after growing and at neutral pH, after growing it, you get some more biomass. Now you can take this slurry, because here after getting the biomass growth, initial turbidity of the liquid will change, because initially you have added only small amount of E. coli, and then due course of time they will also propagate and make more cells, and finally you will get substantial amount of biomass in the liquid. So you'll get a slurry of E. coli and other nutrients. Now after taking the slurry, you centrifuge the liquid. So after centrifugation, you will find a pellet at the bottom of the centrifugal tube, and this pellet you can remove from the centrifugal tube, and then you can check the weight of this pellet. So here, when you try to check the weight of this pellet will still have some water surrounding this pellets, because it is not completely dried. So when you talk about weight, that means you are just trying to measure the weight of the wet biomass. So it is actually not giving the absolute weight of the biomass, because some moisture is still there around the cell, around the biomass. So this is one option to uh, get weight of the biomass. Another option is you take this moist biomass and put it in a plate and then dry it. So you just keep it in air oven. So maybe the temperature would be 110 degrees centigrade, and keep it for 12 hours in air oven. Then the moisture, surrounding moisture will automatically dry it up, and you will get a dry weight. So you will get a dry biomass. So whatever weight you will get for this dry biomass, that will be your dry cell weight. And most of the cases, when you calculate the weight of biomass in the process, mostly we use these two terminologies: dry cell weight, or DCW, and weight cell weight, or weight. But most of the cases we try to use DCW to mention about weight of biomass obtained from specific fermentation process. Now, if you take this dry cell weight, within that you will find this composition: carbon, oxygen, nitrogen, hydrogen. And to estimate this composition, we use a machine called elemental analyzer. So in elemental analyzer, it is a system where you put this dry biomass in a furnace. So you put the dry biomass. First, you take the weight of the dry biomass using a sensitive balance. So we call them as microbalance. So you can actually get weight in microgram in that balance. So first you take the weight of the dry cell biomass, then put the biomass in the furnace, and with the help of excess oxygen, you burn the biomass. So after burning the biomass, it will produce different gases. So it will produce carbon dioxide, because you are providing excess oxygen. It will produce nitrogen oxide. Uh, and then you find moisture, and you will have excess oxygen. Now, in this same system, you have option to monitor concentration of all these gases. So whenever carbon dioxide will produce, you have a carbon dioxide monitoring system. So it will just monitor concentration of carbon dioxide, concentration of nitrogen oxide, concentration of water, or concentration of moisture. So when you monitor the concentration, then you know how much gas you have actually used. So along with concentration, you will get the absolute mass. So suppose concentration is given as uh, say microgram per ml of gases. Now, if you know that you have actually produced 500 ml gas, then you can get absolute mass. So you get absolute mass of carbon dioxide, absolute mass of nitrogen oxide, absolute mass of moisture. Now, if you know absolute mass of carbon dioxide, you can get absolute mass of carbon, absolute mass of nitrogen, absolute mass of hydrogen. So this carbon, nitrogen, and hydrogen actually came from the biomass, dry cell weight. And we are talking about formula as CHON. So if you know carbon content, hydrogen content, nitrogen content, and you also know the total weight of the biomass, then you can easily calculate oxygen content, because total weight of biomass means that is dry cell weight minus carbon minus hydrogen minus nitrogen will give you amount of oxygen present in that biomass. So in that way, you can actually get the weight of all individual component. And when you know the weight, you can easily calculate percentage. So in this way, actually, you are calculating percentage composition. If you know the weight, you can easily calculate percentage composition. And in another way, if you need to calculate the molecular formula, so you know amount in milligram or microgram divided by molecular weight of the individual component like carbon. So whatever gram you will get divided by 12 will give you mole of carbon present. So similarly, you can get mole of hydrogen present, mole of oxygen present, mole of nitrogen present. And after getting this molar value of all individual component, you can actually get a formula like CXHY OZ in W. So these are all mole values. So if you get the mole values, essentially that will give you the formula of this biomass. So you are getting the formula of the biomass with the help of this elemental analyzer. And conventionally, when we try to write this formula, we use most of the cases we use uh, we try to use 1 molar carbon, means the rest of the components are expressed by maintaining 1 molar carbon in the formula. In this case, it will be HY by X, OZ by X, and W by X, and C. So that will be the final molar formula of this particular biomass. So if you know this composition, then it will be easy for you to actually balance this equation, because now you got the biomass formula, so you can easily balance the equation. So different bacteria, they use different kind of uh, material as substrate. So depending upon the metabolic activity, because few bacteria, they can synthesize their own food, they are known as autotroph. Few bacteria, they will rely on some organic or inorganic substances. That's why they are known as heterotroph, because they will not be able to produce, they will not be able to synthesize their own food. They will rely on some inorganic or organic compound. Now, these are this element present in the cell, and these are the possible sources of all these components. So, when you try to grow the bacteria, mostly you will use different sugars as carbon source. We will also have amino acid, so that amino acid can actually have dual effect. So it will directly interact with the metabolic pathway, and also it will provide certain amount of nitrogen. Different cofactors, vitamins, and trace nutrients are used to grow the cells. And also whenever you will have growth of cells, it will also produce the product either intercellular or extracellular. Now, one of the simplest, or you can say general formula or general equation of aerobic respiration is given here. So this this is your carbon source, and this is oxygen, this is nitrogen source, and this is your composition of the bacteria. You have water and carbon dioxide. Now in this equation, you can see the left hand side, we have not written the biomass. Biomass means the same formula should have been incorporated here, but conventionally it is not done because when you do the balancing, the concentration or amount of biomass you get in this left hand side is insignificant compared to whatever biomass you get in the right hand side. So most of the cases, whenever you write this equation, you try to neglect the presence of biomass in the left hand side. You just put everything in the right hand side. The reason is, in any biological reaction, we add a small amount of biomass in the reactor. That's called inoculum. So inoculum is actually the concentration of inoculum is almost zero. Yes, it is. Most of the cases we consider it as negligible. So concentration of inoculum is negligible. That's why suppose you are adding only say 10 ml of biomass, and the concentration in the biomass is around maybe 20 mg per ml. So essentially you have added only 200 mg absolute biomass. Now after doing this reaction, at the end of the process, maybe you will get 2 kg of biomass. Absolute weight, 2 kg. And suppose here it is a 10-liter reactor, so 2 kg per 10 liter. So now if you compare the biomass in the final product side and in the reactant side, then you will see 200 mg is actually insignificant compared to 2 kg. So that's why this value are actually mentioned here. The biomass is in the product side, and reactant side, you just neglect that amount because that amount is insignificant. Now in this equation, when you do elemental balance, like if you do carbon balance, if you do oxygen balance, if you do nitrogen balance, you'll find multiple equations for carbon, for hydrogen, for oxygen, for nitrogen. And then you need to just solve this equation to get all stoichiometric coefficient. So obviously when you do this exercise, you have to make sure that number of unknowns and your equations should be equal. Otherwise, you will have issue with the degree of freedom. So you would either it should not be underdetermined. Overdetermined system is still okay because you can still manage to get values of most of the component. But you have to make sure that when you do this balance equation, number of unknown and number of equation should be equal to calculate all these parameters. So I'm just giving a simple problem to you. You can just solve it here. We're talking about glucose, ammonia, and oxygen are introduced as reactant, and the final you are getting a biomass having this formula, also getting water and carbon dioxide. Now first need to balance the equation, and then it is already given that 2/3 of glucose goes to biomass. So when you try to do the balance the equation, the C is already indicated here through this equation. 2/3 of the glucose C means 2/3 of glucose carbon is going to the biomass. And then you have to calculate stoichiometric coefficient, and then this yield parameter. We mentioned earlier, yield parameter, we always try to get a ratio of product and reactant. So here it is talking about X by S. That means product is your biomass, S is your primary substrate. See, nitrogen is also one kind of substrate, but when you compare this carbonaceous substrate is actually your primary substrate. So then biomass by glucose. So that will be your Yx by S. And most of the cases, we represent it gram per gram. Or if you want, you can use mole per mole. But most of the cases, when you have solid material, we express it as gram per gram. Whereas for gaseous system, it is expressed as mole per mole. So XO2, so X is biomass again, and O2 is here given there. So then just estimate the ratio and then express it in mole per mole.
Sir, can you go back to the equation?
It's not at all difficult because here, this first clue, this two-thirds of the glucose carbon, it is not mentioned whether you need to consider in mass or in mole. So as it is not mentioned anything, you can easily consider it as mole because it will be then it will be very easy for you to calculate the coefficient. So two-thirds of glucose carbon means two-thirds of 6 is 4. So 4. So two-thirds of glucose carbon is 2 by 3 into 6 equal to 4.4 mol C. So that means small c will be 4.4 by 4.4. So you can get the C value, and when you get the C value, you can easily calculate the total weight of biomass. And in this equation, if you do oxygen balance, you will find A value. If you do this nitrogen balance, you will find B value. And if you do hydrogen balance, you will find D value. If you do again for carbon balance, you will find E value. So you can get all the stoichiometric coefficient values, and from this particular exercise, you get the total amount of, if as C is known here, you get the total amount of biomass. You know the total molecular weight of 1 mole of glucose. It is already given here. Molecular weight of cell, molecular weight of glucose, oxygen, ammonia, you know. So you just take the ratio, and that will give you the yield parameter. And as you already got, if you need to express it in molar terms, then it is very easy. For molar terms, y-axis is only small c, because here substrate has 1 mole substrate only. Similarly, x by O2, it will be small c divided by A. So if you know the coefficient, you can easily express in terms of, in molar terms. Only thing is, whenever you express them or whenever you calculate them, you have to make sure that you are using proper unit. If you calculate in terms of mole, then you have to write mole per mole. And if you actually, in true sense, it should be mole of, say, if you talk about the first one, then it will be mole of biomass divided by mole of glucose. In second case, it is mole of biomass divided by mole of oxygen. Similarly, for gram per gram, also gram of biomass by gram of glucose. So you have to make sure that you are giving appropriate unit after calculation. Is it clear to everybody?
Yes, sir.
Good, good. Now, if you see for E. coli, you may try to remember this formula. So using elemental analyzer, they have already estimated the molecular formula of E. coli. So it is CH1.8, O.5, and N.2. That's the molar coefficient of this elements in E. coli. And this is a general formula for biochemical reaction where you get some other byproduct apart from biomass. So again, it is talking about aerobic metabolism. So you use glucose, ammonia as nitrogen source, oxygen, then you get E. coli, and you also get some product and carbon dioxide and water. And again, by doing this elemental balance like carbon balance, hydrogen balance, nitrogen balance, and left hand and right hand side, you will get the stoichiometric coefficients. And obviously, along with this equation, you will also get some other conditions to get this to solve this equations to get values of different coefficients. So number of unknown and number of equation will be equal, then only you'll be able to get all these values. So those relations will be given. Like the earlier case we have mentioned about 2/3 of glucose carbon is equivalent to biomass carbon present in the biomass. So similar kind of relation will be mentioned. Now, if you see the molecular formula, considering molecular formula of E. coli as this, you can easily calculate molecular weight. Now, if we consider it also has 5% other trace nutrients, other trace materials, then actual weight would be, actual molecular weight would be, because this 24.6 molar mass actually contributed by 95% of component. So actual molecular weight would be the molecular weight of 100% material. So to know actual molecular weight, you just take this value divided by 0.95. So that will give you the actual molecular weight of 100% component. So in this case, we are considering 5% trace nutrient present in the system in the E. coli. And considering the major nutrients, if you get molecular weight as 24.6, then actual molecular weight, or for 100% material, the molecular weight would be 24.6 divided by 0.95.
So shouldn't it be into 0.95 if we're considering like 5% is extra?
No, then just simple arithmetic equation. So 0.95 gives weight of 24.6. So what will be the weight of one unit? That would 24.6 divided by 0.95.
So but this 24.6 includes that ash weight contributed by the other
No,
inorganics, right?
no, you're not. You're not considering that, no. So if you just simply you calculate molecular weight considering this formula, then only you'll get 24.6. So here there is no presence of any other ash or other component. 24.6 you are getting from directly from this formula. And this formula is representing only 95% of biomass. 5% is actually your other organic content, which is also known as ash content. So because when you burn it, all other inorganic compounds will produce different oxides like MgO, calcium carbonate, or sorry, calcium oxide, different other
Fine, sir.
oxide.
Understood.
So you will get actual molecular weight. So when you try to calculate the overall product weight, in that case, you may need to use this actual molecular weight to know overall product weight. So in process design, mostly they will talk about five, say as I mentioned, maybe they will just mention about formula plus ash content, say 5% or 2%. Accordingly, you need to actually calculate the actual molecular weight. So this is all about your this generalized growth equation. I hope you could now realize the importance of the molecular weight of the biomass, because if you know this, then only you can actually get if you know this, then only you can get the, means you can do the equations, the balancing of the equation, and then you can calculate all the stoichiometric coefficients. Now, again, another example that you can solve as a homework, maybe. So it is again given the concentration of the final biomass. You need to grow 50 gram per liter concentration in 1 lakh liter reactor volume. So you can calculate absolute amount of biomass, and then you can calculate, because here all of the coefficients are given. So you can get a balance equation. First, you try to see whether it is balanced or not. If it is not, then you have to just balance the equation, and then you need to calculate mass of glucose, ammonia, oxygen, and all these yield parameters. So you can just consider it as your homework and then try to solve it at home. Now, in bioprocess or chemical process system, we need to define the process using a flow diagram. So in your second year, your computer science courses, you must have done some exercise on preparation of flow chart. So in flowchart, you try to see the logical flow of specific argument to get a desired outcome. So you have used different kind of logical argument, like either yes or no, or if you have some other conditional operator, then you use them. You have used the conditional operator, and then finally you just arrive to a specific outcome. So similarly, in chemical process or bioprocess, you have raw material, and then from raw material you try to get your final product. So the raw material could be, suppose you are trying to uh, produce bread from wheat grains. So here your raw material is wheat grain and your final product is bread. So obviously this wheat grain will actually get processed through different operation, and finally you will get the bread from the wheat grain. So the entire process cycle from your raw material to achieve the final product can be depicted in multiple ways. Means you can actually provide the process information by putting some boxes. So these are different blocks, and you can put arrow between the blocks, and finally you can get your final product. So you can represent this process using this block diagram. Sometimes it is known as input output diagram. So there, anybody by just seeing this block diagram will be able to understand that, okay, in this process, so many unit operations are there, and then you are getting your final product. So using block diagram, you can just give some description of your process. But the block diagram will not give too much of information. It will just show, suppose you are washing the grain. So it will just give a washer. Maybe then you are grinding the grain, then you will have just have a grinder. Then you may have a screen to just separate larger size particles. Then you will get five screen. You can have fine screen, you can have coarse screen. Then you will have a unit for making a dough, then dough making unit, and then you have a system to actually add other additive to the dough, and then finally you'll put it in the oven, and then after oven you will have, you can say maybe you'll have option for baking operation, and after baking the process you will finally get the final bread, and after getting the bread you will also send it for packaging, and after packaging you will get the final packaged product. So in the block diagram you can just give roughly some, you can get rough idea about the process entire operation, but you will not know the exact amount or exact chemical processes happening in different unit operations. And also you will not have much idea about what kind of process line to be used, whether you need to use a metal conveyor belt, whether you need to use a rubber conveyor belt, whether you need to maintain certain temperature in a specific unit operation, whether you need certain moisture or certain pressure in this particular system. So you will not have detailed idea about different units involved in this entire process. Now, as an engineer, when you try to implement, suppose if somebody has asked you to build a plant for making this bread. So there, mere having this idea about the different unit processes will not help you to actually implement or design or set up a full-fledged plant. There you need more details in all connecting lines, like how much amount of raw material is required in this process, how much amount of raw material will get wasted in this process. All this detail should be there with you, then only you'll be able to actually make a complete or you can set up a production unit based on this diagram. So for engineers, this diagram has significant value, and this block diagram is, you can say, the first level of exercise where you can get gross idea about the process. And they're also known as input output model. So it will actually show what kind of parameter is going into a specific box and what are the other output parameters coming out from the boxes. Now you can get little bit more elaborate diagram if you just use this functional diagram. The functional diagram is actually talking about some sort of functions involved with unit processes. So here, each box here we are talking about, suppose we are talking about washing. You can have different kind of washing mechanism. You can have a simple water tank and then a mechanical washer to just create vibration. You can have water jet flow washing the flowing solid from the top. So different kind of washer you can have. So the functional diagram will actually define a specific type of washer you are using for washing the solids. Similarly, for grinding, whether you are using ball mill, whether you are using any other grinder. So all these details will be given in the functional diagram, but still it is not giving complete details of all the input output parameters and also conditions maintained in unit operations. So when you talk about complexity, then obviously the simplest thing is input output diagram. Then you get little bit of complexity in the diagram by mentioning the function of individual unit. Then you can have operational diagram. There they will talk about different technology used in all unit boxes. And finally, you can get process flow sheet or process flow diagram where this input output parameter, their values, their conditions, everything will be mentioned. But when you try to implement it, then you need to go for piping and instrumentation diagram, or so we call it as PNI diagram, piping and instrumentation diagram, where each and every line will have some significance. It will actually mention what kind of material to be used to make this pipeline, what kind of temperature, what kind of insulation is required in this line. Everything will be mentioned in the diagram. So I'll just show you the diagram, then actually you will have a little better understanding about the complexity and their requirement. So first you have the process flow sheet that will just show the logical flow of the material from the initial unit operation to the final product process. So it is as an engineer, first you need to make the process flow sheet. So it will be your process flow sheet. You cannot put the washing after baking the bread. So washing would be the first step. Then you will have grinding. Then you will have screening. So logically, you need to put all this unit one after another, and then you can get a process flow sheet. This process flow sheet is actually talking about the logic behind the specific process. You are not actually getting any other more information from this. Then you get functional diagram. So again, I just tried to combine the input output block diagram and functional diagram together. So in this block diagram, all these unit operations are kept in separate blocks, and you can just put different kind of input parameters required in individual blocks, and you can get actually a little bit more details of the process where you provide all other nutrient, all other parameters in a given box, and finally you can get multiple input, single output. Similarly, another box you can get single input, single output. So here, at least all these unit operations are well defined in terms of input output parameter. So after getting functional diagram, you will now get operational diagram where you will actually mention about the, the temperature and pressure you need to maintain in different blocks, but still there block diagram. Then you will get process flow sheet where you will actually use different kind of symbols for different unit operations. So if you use heat exchanger, you will have a different kind of symbol. If you use reactor, you will get different kind of symbol. And there you will also try to maintain, although in this diagram we have not mentioned, but also you will maintain the amount of flow. So suppose you need to use certain amount of benzene, that amount of benzene will be mentioned here, and amount of possible sludge production will be also mentioned here. So in process flow sheet, you will actually get all input and output parameter well defined in terms of their masses and energy usage. Then you will get finally piping and instrumentation diagram where this masses and flow rate will not be mentioned, but it will talk about, you can see different symbols are there, and also different terminology is mentioned, like here 3-inch schedule number 40 CS. So it is actually talking about a specific configuration of the pipeline. So the pipeline diameter would be 3-inch diameter, and the type of the pipe will be schedule 40, and material of that particular type pipeline would be carbon steel. So if you need to use stainless steel, then it will use SS. So different kind of terminologies are used in PNI diagram, and there also mostly in terms of control and automation, this diagram is quite useful. So material of construction, control operation, all these symbols has some significance. So if you just check terminology used in PNI diagram, then you will find different standard nomenclature used for defining this PNI diagram. So this is useful for the engineer, and this process flow sheet is also useful for the engineers. So the control engineer will actually use PNI diagram to define or to use appropriate control strategy to run the process, and chemical engineer will also use this process flow sheet to know exact amount of material required to do a particular operation in different unit operation in the entire process. So is it clear to everybody?
Yes, sir.
Yes, sir.
Okay, fine. So I'll stop today here because it is already 12:54. So next class we'll discuss about little more about the process system, and then we'll give some example. So I'll stop here today. Meanwhile, actually, I talked to during the class also. I just talked to one of our faculty members, and I discussed about this prerequisite issue. So he suggested it is better if we just offer it for 2019 entry student. So 2020 entry student, as per your class schedule and your course schedule, you will get chance to do this course in next year. So I'll request all 2020 entry student to drop the course now, and they will take this course as per their course schedule in next year. So this time we'll just offer it to the 2029 students, and all 2020 entry students, please deregister and just wait for your turn in next year. So those who are present here, just take a note of this, and if 2020 entry students are not here, I'll request the students, those who are here, they just convey that message to the 2020 entry student that they should drop the course now and they just wait for their turn next year. Okay. So see you again on Tuesday.
Thank you, sir.
Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.